Section 11.1, Approximating Functions with Polynomials, mostly known as Taylor and Maclaurin Polynomials. Well, first of all, what we're going to do in this section, in the new chapter, it's to find polynomial approximation of elementary functions. And then we're going to use the Taylor remainder theorem to determine the maximum error in the approximation. But, well, we're going to leave this topic to the very end of this chapter. Alright, so what's the basic idea about this polynomial approximation? So back in Calc 1, you did what we call linear approximations. Alright, and all you did is basically find the equation of a tangent line at a given point. For example, you were asked to find a linear approximation for the function e to the x and make it look like, well, this is a f of f of a plus f prime of a times x minus a. So that was pretty much the idea of the linear approximation. And then you use this linear to compare with the graph of the exponential function. So the idea here is that around the center, so for example in this case we do the approximation of the exponential function at 0, we're finding the equation of the tangent line at x equals to 0. So now around 0, see how other values are pretty close to the actual value, you know, so from the value on the linear function and the value on the actual function. For example, I think, you know, if I look at this interval right here, from here to here, we have very close values from both on the line and on the curve of the exponential function. However, if I wanted to use the linear approximation to say approximate e squared, that is, I would have to evaluate it at 2. Well, maybe not that. Maybe e to the first. Well, do you see that right here that the values for both on the linear function and the curve, they start to kind of diverge? You know, they're no longer as close as possible, the actual versus the approximate. So in this case, well, we will have to do something else. And well, that something else is called to use a Taylor polynomial. So this idea of the linear approximation can be extended to come up with not just a linear approximation, maybe a quadratic approximation, a cubic approximation, a quartic, quintic, sextic, your favorite approximation, with the end result that the more terms that you add to the polynomial approximation, a more accurate approximated result you would get. For example, here on the second picture right here, we have the graph of e to the x on pink, and in this case we have not the linear approximation but the quadratic approximation. Now, as opposed to the linear approximation, so if you remember, well, the values are closer to one another for this very small range of values. Nevertheless, here the quadratic approximation makes this range a lot bigger, so we can approximate, I don't know, maybe what's this, perhaps negative 3/2, no, negative 2/3 rather, maybe negative 2/3, and over here this is maybe 0.5 or 1/2 rather. But over here it's barely like a third, and this looks more like a fifth. I don't know. It's a very small range. So the quadratic approximation helps us get a better approximation for a wider range of values. If we keep going, and if we perform instead a cubic approximation, all right, see how the cubic approximation is a lot closer at more points to the actual value of the function. And even better, check this out, check the quartic approximation. Look how the two graphs are almost identical, except for these mini gaps right here, but we can use a quartic approximation centered at 0 to approximate more values, pretty much from -2 to, I don't know, I'm gonna say 2. All right, as opposed to a smaller range here from what was that, 3/2 to 1/2. It's a very limited range. So the more terms that we add to the approximation, the better range of values that we can use to approximate this. All right. Now, this is called the Taylor Polynomial piece of n, and well, what we do is evaluate the function at the center value plus the first derivative evaluated at the center value times x minus a. So this part right here, you might remember it from calculus 1. That's the linear approximation. These new terms right here are the new terms, are the terms that will construct the quadratic, the cubic, the quartic, quintic, etc. All right. So in this case, well, we are finding an approximation of the polynomial approximation of a function centered at a value c. All right. And well, of course, if we write this using the sigma notation, that's what we're computing here is the nth derivative for depending on the order of the polynomial that we want, and this is how it looks like using sigma notation. However, on the other hand, when we center our approximation at 0, it has a special name. It's called a Maclaurin polynomial, as opposed to the Taylor polynomial, when the center is a value of c different than 0, centered at 1, centered at 2, etc. All right. So how about we look at one example? So let's find the linear, the quadratic, and the quartic polynomial approximations for e to the 2x centered at x equals 0. So the fact that this is centered at x equals to 0, well, this means that we're finding a Maclaurin approximation, Maclaurin polynomial. All right. So number one, okay, so we need to find a few derivatives here. So let's see. So we're going to start with the original function f of x, e to the 2x, and then we're going to evaluate f at the center values, because in this case the center is 0. Well, this is e to the 2 times 0, which is e to the first, e to the 0, which is 1. Let's take the first derivative, f prime. That's going to be 2e to the 2x, and evaluate this derivative at 0 also. 2e to the 2 times 0, and that's 2 times e to the 0, which e to the 0 is 1, 2 times 1 is going to be 2. Second derivative, that's 2 times 2e to the x, that's 4e to the 2x. Evaluate the derivative, the second derivative at 0, and that's 4 times e to the 2 times 0, which is 4. And then let's take the next derivative, the third derivative. That's 4 times 2, that's 8 e to the 2x. F triple prime evaluated at 0, that's 8 e to the 2 times 0, which is 8. And one last derivative, because we want the quartic polynomial. That means we need to find 4 derivatives. F, recall that the notation for derivatives higher than 3, we no longer use the prime symbol. We open parentheses and put the number inside of the parentheses. That's to denote the 4th derivative. And 8 times 2, that's 16 e to the 2x. F quadruple prime at 0 equals 16 e to the 2 times 0, which equals 16. So we have all the information that we need to, in this case, find the polynomial approximation for the exponential function, that is the Maclaurin polynomial. So, well, what do we want in this case? So we recall that this is an infinite series. I mean, if we have infinitely many terms, well, then that's actually the given function. But in this case, well, this n is finite. Yes, we're not going to find infinitely many terms. We're not going to find 150 terms. So we're going to use the fourth degree approximation. First of all, let's denote what we're going to find. So p sub 4, this p sub 4, that denotes p of 4 polynomial, and the sub 4 denotes the degree of the polynomial. So that'll be f of 0 plus the first derivative evaluated at 0 times x minus the center. Let me write x minus 0. I know it's kind of absurd to write just minus 0, but that's just to illustrate how the center looks like, plus f double prime evaluated at 0, x minus 0 squared, the whole thing divided. That's where we start dividing by the factorials. The factorial, well, technically this is a 1 factorial, but 1 factorial we know it's 1. This is a 0 factorial technically, which is also 1. So that's why I didn't write them in the first place. It's fine if you don't write the first two. The one that we start writing first, if it's fine, it's the second, from second and on. And then plus f triple prime evaluated at 0, x minus 0 cubed over 3 factorial plus f quadruple prime evaluated at 0, x minus 0 to the 4 power over 4 factorial. All right. If they asked us to find the 6-stick polynomial, well, we would have done 2 more derivatives and add 2 more terms to the polynomial. So we have everything that we need. Let's highlight so you can see how we're going to connect this. So this f of 0, which is 1, it's this one right here. And then this f prime comes from here, f prime, evaluated at 0. Okay, let me color this one as well. And then different colors. Okay, this one is fine. And this f double prime, and what else? Any other cool color? Okay, let's see this one. That's gonna be this third derivative, and finally, I don't want to use another blue. Maybe a green. Okay, this green is fine. And 16, it's f quadruple prime, which is this f quadruple prime. Okay, this last one might be a little bit hard to read, but it's fine. Okay, so now that we set up what we're going to write, so f of 0, which is 1, plus f prime of 0, which is 2, times x minus 0, plus f double prime, which is 4, x minus 0 squared over 2 factorial, which is 2. And let's leave it in terms of factorials for now. Yes, why not? And 4 over 2 factorial, and plus the third derivative, which is 8, times x minus 0 cubed over 3 factorial, and plus 16 x minus 0 to the 4th over 4 factorial. Okay, So let's simplify this polynomial. Let's see, yes, all right. So P4 will be, in this case, 1 plus, okay, I'm no longer writing this minus zeros, so I'm just going to write 2x plus 2 factorial, which is 2, 4 over 2, that's going to give us a 2x squared. And then 8 over 6 factorial, so I mean over 3 factorial, which is 6, that's 8 over 6, which reduces to 4/3 x cubed, and 16 over 4 factorial, but 4 factorial, I believe, so 4 times 3 is 12 times 2, that's 24, 16 over 24. 16 over 24, which reduces to 2/3 x cubed, oh no, x to the 4th. And that's our P4. But okay, in this case, they're asking us to list the first, the second, and the fourth one. So what we're going to do, okay, let me first move it down. Well, let me actually leave it where it was. That's fine. So I also need to write piece of 1, which represents the linear approximation, that is the first two terms. And they also asked us for the quadratic as well, p sub 2, which is the first three terms. And those are our approximations here. All right. Now, part B of the problem. So they're asking us to find, to use this quartic polynomial to estimate the value of E. All right. How we're going to find? How we're going to do that? Well, so use P4 to approximate the value of E. All right. Well, so in this case, what we're going to do, yes. Well, notice in this case we have be careful here, because as our f of x equals e to the 2x. So we need to use. So we're going to use the value of P4 in order to, or the polynomial P4, plugging in a convenient value that approximates E. Now, if we use the original function to get the accurate value, which value of x should we plug in so that the output right here is simply E? All right, think about that. What number would that be? Should it be 1? Well, if x equals 1, well, then f of 1 equals e to the 2 times 1, which is e to the 2. Well, that's not going to give us e to the 2. So in this case, we need f of 1/2. F of 1/2 would be e to the 2 times 1/2 reduces to 1, and that's our E. So evaluating this P sub 4 at 1/2, that's going to be, well, 1 plus 2 times 1/2 plus 2 times 1/2 squared plus 4/3 times 1/2 cubed plus 2/3 1/2 to the 4th power. And while using a graphing calculator, we can simplify all this. That's going to give us approximately 0. Actually, no, not 0. That's 2.708, which is a good approximation because the value of E is 2.7182 and many decimals. If we compare these two results right here, this one and that one, I think the 4th-degree approximation does a pretty good job. All right. So let's look at another example. So I had this blank page. Okay. So let's find the 5th-degree polynomial for f of x equals ln of x, centered at c equals 1. That means in this case, because the center is not 0, the center is a number other than 0. This is a Taylor It's a Taylor polynomial. Alright, a Taylor polynomial as opposed to the Maclaurin polynomial. Okay, which is when the center value is at 0. So let's start doing the same as we did before. So f of x equals ln of x. Let's start with the function. And then evaluate the function at 1. That is f of 1 equals ln of 1, which is 0. Take the derivative of ln x, that's 1 over x. Evaluate f prime at 1. 1 over 1 equals 1. Find the second derivative, but be careful when evaluating the second derivative, because, well, we need to write this as x to the negative 1 instead. And the derivative of x to the negative 1 will be negative 1 negative x to the negative 2, which is the same as saying negative 1 over x squared. Alright, now evaluate the second derivative at 1. That's going to be negative 1 over 1 squared, which is negative 1. Let's take the third derivative. In fact, we're going to take all the way to the fifth derivative because we want the fifth degree Taylor polynomial. So let's take it from here. Negative 2 times negative 1, that's 2x to the negative 3. Let's write it the other way because we need to evaluate it as well. F triple prime evaluated at 1. 2 over, oh, that's supposed to be cubed. 2 over 1 cubed, that's 2. Let's keep going, the fourth derivative. So that's 2 times negative 3, that's negative 6, x to the negative 4. Negative 6 over x to the 4th power. F quadruple prime evaluated at 1, that's 6, or rather negative 6 over 1 to the 4th, negative 6. F, the fifth derivative, evaluated at, oh no, let's find the derivative first. So that's 6 times 4, that's positive 24. X to the negative 5, which is 24 over x to the 5th power. F quintuple prime evaluated at 1, that's 24 over 1 to the 5th power, which equals simply 24. And just like before, we have all the information that we need to write down the polynomial approximation for ln of x centered at c equals to 1. Alright, let's set up the formula first. And yes, this one is going to be a long expression. Something that you might have realized at this point is that these problems, these exercises are tedious, you know, because of what we write. It's more the writing that we do than really the computations. And it's important to have every single step, you know, so it's clear when it comes to debugging in case something doesn't check or something. Plus it looks great. Well, that's where the 2 factorial plus f triple prime at 1, x minus 1 to the 3rd over 3 factorial plus f to the 4th derivative, not to the 4th, at 1, x minus 1 to the 4th, 4 factorial plus f quintuple prime evaluated at 1, x minus 1 to the 5th over 5 factorial. So that's what we're going to write So, and again, you might want to refer to these coefficients the same way we did. I think I'm not going to highlight, I'm just going to highlight real quick. Okay, so this f of 1, oops, nope, that's not what I meant. So this f of 1 is this f of 1. This f prime of 1 is this f prime of 1. This f double prime of 1 is this f double prime of 1, etc. All right? So just refer to the results, and of course I'm going to start writing this. So p sub 5 of x equals f of 1, which is 0 plus 1 times x minus 1 to the first power. Yes, in this case I'm writing those invisible ones just to make more sense about it, and so you can see where they're coming from. And then that's going to be minus 1. Be careful, because that was a negative 1 times x minus 1 squared over 2 factorial plus 2 times x minus 1 to the third power over 3 factorial, minus, and then minus 6 x minus 1 to the 4th power 4 factorial plus 24 x minus 1 to the 5th over 5 factorial. Okay, so let's start simplifying this. So how do we simplify this? So this 3 factorial, 4 factorial. Okay, so if we break up this, okay, let me use a different color here, just so you don't use calculator. So 3 factorial is it's 2 times 2 factorial, all right? This 4 factorial is the same as 4 times 3 factorial, and this 5 factorial is it's 5 times 4 factorial. But guess what? Don't you see how don't you see how this 4 factorial is the same as this 24? We can cancel those. This 3 factorial is 6, which cancels that 6. 2 factorial is 2, which cancels this 2, etc. Well, actually, just stop here. All right. So so p sub 5 of x will be x minus 1 to the first power. I'm going to keep writing that 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed minus 1/4 x minus 1 to the 4th plus 1/5 x minus 1 to the 5th power. All right, so that's our 5th degree approximation to the function ln of x centered at 1. All right, so let's see what the approximations are over here. Well, so approximate ln of 1, or I mean ln of 1.5. All right, so here's what we're going to do. Well, number 1, let's write it down. And so p sub 5 evaluated at 1.5 equals, okay, so what happens, so because I really don't want to write the whole thing, so what we're going to do is write this 1.5 at every instance of x. All right, that's what we're going to do. But what happens when 1.5 gets subtracted by 1? Well, that's going to leave us with 0.5 inside of the parentheses. So and I'm going to take advantage of that to shorten the steps right here. So that's 0.5 to the first power minus 1/2, 0.5 to the second power plus 1/3, 0.5 to the third power minus 1/4, 0.5 to the fourth power plus 1/5, 0.5 to the fifth power. All right. So, well, so if to simplify this using the graphing calculator, well, instead, okay, let me show you what happens, what's really the bigger picture of this. So in a similar way that we did with the exponentials, remember the first picture when we compared the exponential function with the linear approximation, the quadratic, the cubic, the quartic. Okay, so here it turns out that in the graphing calculator I have y1 ln of x, and I type for y2 that approximation we just obtained. Okay, so let's look at the graphs. Let's graph. And do you see how at a certain interval the approximation, which is in red, it's very similar in the graph, or rather overlaps the blue graph right here, which is the ln of x. So for example, in this case we want to find the value for, okay, so let's see, second, let's find the value for 1.5. all right, okay, so notice how we're getting this value 0.4054651, etc. But notice how the two values are pretty much the same, you know. So let me see if I can, well, did you see the difference? 407, 405. So I think the quintic polynomial right here, the quintic approximation, does a pretty decent job in approximating the values. Now here's the thing, and this is, you know, like the bigger picture of what these approximations are. Now, what if I wanted to approximate instead? Okay, let me do, okay, second value, and let's see, 2.3. all right, how about 2.3? Okay, so on the natural log function I'm getting which is the actual value, that's 0.8329091. that's the actual value. But let's have a look at the approximated value. Do you see how far off is the approximated value from the actual value? It's not a good approximation. Well, so there's a couple of ways that we can do to obtain a good approximation for 2.3. Number one is to do the whole process of taking these 5 derivatives, but instead of centering our value at 1, we will be centering it at a closer value. How about at 2? That's going to do a pretty better, pretty much a better approximation. That's one solution. The other solution is keep using the polynomial centered at 1, but not stopping at the 5th degree. Maybe add 2 more terms, the 7th degree, the 8th degree, the 9th degree, etc. Those are the 2 ways. All right. So I think this picture summarizes the whole purpose of this section. Okay. Let's go back and do another example. All right, so let's find the 10th degree Maclaurin polynomial for cosine x, and then use this polynomial to approximate the value of cosine 0.5 and compare to the actual side. But I think I'm going to leave this exercise for the next video.